Hello everyone, we're going to start. Welcome. I'm not sure if we need the microphone actually, but for now, while we're still getting seated and enjoying the pizza, I will just use it. So, thanks all for coming. I hope it will fit. There is around 150 seats, so it should work. But try to maybe move to the spaces where there's still space left, because it's not as easy to go and find the middle ones, the empty ones. So yeah, let's just start out. So my name is Roelof. I work as a data scientist, mostly consulting, and I do a part-time PhD at KTH. And I have a big love for data. So that's why I thought, why not start another data science meetup? Well, I'm a big fan from the recently started natural language processing meetup by Sahar, also here from Meltwater, and also from the one always thrown at Spotify. Of course, more is always better, also with data, but also with meetup. So why not try another one? So there we go. This one being about deep learning. A new exciting branch of machine learning. So I'm kind of used to give a lot of talks on deep learning, but for today I will try to shut up. So I give the words from people who actually have been doing this already for a couple of years, much longer than I have. So yeah, this is the Wi-Fi and the Wi-Fi password for those who want to connect or share stuff around on Twitter or whatever. It's also on the walls. About the pizzas, there's big pizzas, of which some people hopefully found out which ones are vegetarian. There's the smaller ones, which are vegan and gluten-free. And there's also beer and coffee. So yeah, the meetup, it was founded a couple of weeks ago, and already 209 members and counting, so more than I was expecting anyway. So quite exciting. To spread the news of what we're doing and why, inspired by our Stockholm Tech. Try to share some of the stuff with Stockholm DL, Stockholm Deep Learning, so we can spread the stuff around and tell people what Stockholm is also doing with machine learning. And all the upcoming events, this is a bit long to type in. All the upcoming events will always be also at this shortened URL, so that's easy to share. They will always be changed to the new event. This is how it looked. We started, I started I think on a Sunday or whatever. And then at some point people found out and we immediately boomed to 160 members. And now we're at 200 something. This is where we decided actually on the date. So somehow already 75, almost 100 people were so excited that somehow they already signed up RSVP when the date was not yet set. And then actually it continued instead of going down. So the idea about the meetup, and again, this is all under, I hope something will work out through the more meetups which hopefully will become. But the idea, at least, I was having with this meetup and also talking to more people who would be interested in presenting, etc., to organizing every monthly-ish. So it might be a bit less or a bit more, we'll see. Venues for up to 150 people, maybe a bit less, maybe a bit more. We'll see what works. It's a pretty big crowd. It's nice to keep these things a little bit informal as well, but also kind of, yeah, filling the needs apparently for people who want to know more about this kind of machine learning things. So we'll see if this is not a too big crowd, and hopefully we'll have some discussions as well going on. So it's based around guest speakers, so we'll try to invite like different people working already in the field of deep learning, or who have started with deep learning and maybe on their troubles and hassles along the way, from different levels. It can be more technical, it can be sometimes a bit more business inspired, so we try to switch a bit between these things, and it could just as well be that we'll have some smaller, more hackathon events or others with different kinds of crowds, but we'll see how that works out. It's open to anyone, so both academia and industry, and we'll try to kind of mingle a bit in that way. Interested in, yes, this family of machine learning, which we call deep learning, as we'll find out what it is. But basically, it's a new distributed way of representing knowledge and doing what is also called representational learning. So instead of doing a lot of manual feature engineering, you kind of let the machine learning algorithm take care of the features as well as the output. We'll see more how that works. And I hope that it will be a collaborative open space, so let the beers and the pizzas help with that, where we can just share our ideas and knowledge, and also maybe set the field for new exciting research projects or whatever, or as in industry or in academia, and just hang out and have fun. Yes, of course, as I am data scientist, I threw something together with a Meetup API. So this is just who we are, at least the ones who had pictures on their profile. So it looks a bit crappy. There are some black things missing. It's all like through, I think, a few lines of code. So that's what it ended up with. And me in the middle, that's by mistake. It's not that it's made for real. It's just that my name, Rudolf Peter, somehow is somewhere in the middle in the alphabet, or at least. So believe me, I hope. So if I would be Anton, I would have maybe ended up top left. So yeah, this is today's schedule. We're a bit over schedule already, 10 minutes. But basically, yeah, the welcome, that's what I'm doing now. So welcome, everyone. We have a few words from our two sponsors who made it all possible. So thanks to Agafy and Meltwater that we're here, and that we also have some food. Then we'll move on to our first talk with Stefan Carlson, who will introduce more later, but who is a professor at KTH at the Computer Vision Lab. We'll have a short break, pee break as well. And then we have another talk by Josephine Sullivan, who is doing also deep learning, computer vision, and works in the same lab as Stefan Carlson, and who is an assistant professor or assistant teacher, lecturer. And then we'll have another hour for those who want to stay behind, to mingle, etc. Any questions till now? No? Good. Then it's all very clear. So today's speakers, I will shortly already say a bit about them. Stefan Carlson, the talk Deep Learning in a Nutshell, Professor of Computer Science and Director of the Lab for Computer Vision and Active Perception, also called FAP. He's a PhD in communication theory, and his research interests are also in computer vision, in 3D visualization, and in also all kinds of connections with object scene and action recognition. So he's leading the FAP lab, and they're doing a lot of really exciting things there at KTH. As far as I know, they were the first one in Sweden to start using deep learning, if I'm correct, at least in the research setting. So they have been working with it, so that's the people to ask. And Josephine Sullivan will talk more specifically on deep learning for computer vision. And she's assistant lecturer and postdoc also at FAP. And a doctorate of philosophy from Oxford University in engineering sciences, and also works on computer vision and mostly visual tracking and pose recognition. Do we have more? Yes, there we go. A word from our sponsors.
You want me to go first? You suddenly made me go first.
You go first.
How long have we got? 4, 5?
What do you want? You got the crowd.
Yeah. Give me that. I don't want that.
And then you want this.
I was hoping to block the video. I don't like being on camera.
We have a live recording on Google Hangouts, but don't worry, it's only the people who are there who record it. But they can hear you. So. No.
It's this connector. It's a bit off.
Yeah.
Is it there?
No signal yet. Some connection trouble, it seems a bit.
Put it there. There you go.
There you go. There we go.
Okay, guys, I'll be really quick. My name's Jay. I'm the founder and chief scientist, CEO of Augify, a small data science company. We're creating the next generation of what's called real-time intelligence applications. We do two things: data science cloud, which we sell to our clients on a monthly basis to solve some complex problems in data science. And then we have a narratives cloud that enables us to do interactive and immersive storytelling and to do next generation data visualization. Some of the people that we're working for right now, I'll just touch on a couple of those projects in a second that might be quite interesting. Walmart, the United Nations, Capgemini, Phillips 66 are some of the types of organizations who work with us. And what we're doing is large-scale news and media monitoring. We're doing patent analysis, network detection. We're doing particular projects about fraud analysis. So we're handling a $1 billion intellectual property theft at the moment, trying to work out through all the connections possible in the world where these people are using this stolen intellectual property. We're doing large-scale social media monitoring. We're doing some Chinese political network analysis, USA political network analysis, trying to understand how people are connected across the planet and work in certain ways, both in business and politics. And for Walmart, some hyper-immersive visual environments, so floor-to-ceiling, 360-degree rooms where you have every single piece of data for the organization coming through the system, visualized, analyzed in real time so people can interact and understand it. So the platform itself enables us to do lots of different things, from harvesting data, thousands of different sources that we harvest data from, understand data, and then clean that data for analysis in real time. So cleaning for us, first of all, and then we do some meaning-based analysis, so how we do text analytics, search analytics, network science, object recognition, vision recognition, and so on, lots of image analysis work in there. So these are some of the algorithms that are in our platform. Give you an idea of the types of things we analyze, so people's intentions to buy, to sell. For the United Nations, what political emotions are being sensed in real time, feelings of fear, safety, freedom, justice, entitlement, financial emotion analysis. We do other stuff like what we call things, entity detection, entity recognition, disambiguation, whole bunch of algorithms. So essentially with our platform, we sell the clients access to data, algorithms, visualizations. We give them a monthly bill, and we're sort of outsourcing their data science problem for them. So once we've understood the data, we create narratives, so visual views against that data for flows, time, networks, statistics, proportions, hierarchies, all types of visual views against that data to create the narrative. And I'll quickly flip through these. Some stuff for Walmart for what's happening in real time for social, some analysis of networks about how people are talking about shopping, what their intentions are within the network. You see some other pieces for Walmart there. This one's a view for the United Nations where we're tracking sexual violence, government fraud, terrorism, all sorts of corruption-based issues in developing nations in real time. So part of this is how we can track topics that people talk about. We do that in 20+ languages, so all the European majors, Asian languages, Arabic, Farsi, etc. So we do those types of things. Some more here for political network analysis, political network intelligence for the UN for human rights violation analysis. And I'll flip through these quickly. You can see volumes of activity. You can see maps of topics and how those topics are being talked about in real time. Once again, volume. We do competitor analysis of topics that people talk about for main competitors for certain organizations. Network detection, volume, the peaks and troughs of activity of whether it's hashtags, sentiment, emotion, topics, all of those things. And more stuff for Walmart. Some analysis of social topics and activity over time. And then some network analysis that we do. So basically we have lots of visual views against all of this data that we analyze in real time, that we add meaning to with the algorithms that we use. So whistle-stop tour about what we do, but just want to say one thing about deep learning. We're heavily engaged in working on some deep learning projects right now. These are our challenges. These are the big things that we're working on. So events, prediction and virality of events, temporal event causality. So how we can understand what may happen, what's the cause and effect of things, how is time related to particular mentions of particular organizations, particular emotions. Text understanding in many languages, and that's one that holds great promise for us with deep learning, where we can say we can do good text understanding in many languages more easily than we do it right now, where we've got lots of languages that we have to support. We have to go through a lot of hard work to support those languages. And then finally, truth and rumor detection, so understanding where truth propagates through networks and where rumors propagate through networks. And then some audio transcript analysis. So that's what we're working on. I want to bring one thing to attention, which is that we're doing a data challenge. I hope you can all follow us on Twitter and see when this data challenge is. We have some prizes. The challenge is with the Singularity University, Stockholm Resilience Center, Swedish Academy of Sciences, the Bayer Institute of Ecological Economics. We're looking to visualize network risks for a data set that we're going to give out, and then find new novel ways to understand those risks for the Anthropocene. So that's it. I just want to keep it quick as a sponsor who's coming up into the chat. Any questions, ideas, interactions, anything you want to talk about, please grab me after. And if you please follow us on Twitter and boost us up now for 20 followers, that would be great. Okay, thanks guys.
Mm-hmm.
Yeah. Right.
Come on, Mike. Where's Mike?
Hello, everyone. My name is Sahar Asadi, and I'm from Meltwater. First of all, I'd like to thank Roloff for his great initiative and his energy and dedication for this event. I'm really happy for having this event, and I know how hard it is to start a meetup, so great job. So we are one of the sponsors of this meetup, and I would like to talk very shortly about our company. So some of you have been already in the NLP meetup, so probably you know many of this stuff. Anyways, Meltwater is originally a Nordic company, originated in 2001 in Oslo, and the headquarters at the moment in San Francisco, and we are quite a widely spread company. We have over 50 offices around the world, and here you see some of the spots where we are located. And we have, these numbers are a little bit outdated, but we have over 35,000 clients and around 1,000 employees. And well, I mean, the company was originally a sales-driven company, and for selling products related to media monitoring. That's originally what we do. And in the past 3-4 years, we focused more on the tech side and trying to develop offices are mainly located in US, Germany, Sweden, Hungary, and India, and we closely work every day together. So the original idea was that while a customer is taking the morning coffee, opening the laptop, has already some idea of what daily concern that that customer has. We try to provide within that time that this person taking the coffee, provide analysis of what's going on viral in the world related to the concern of that person. For instance, let's say that what are the products reviews related to this company's product? What are the what is going on in their own industry? What is like geographical changes of interest of people in specific products, how it goes for the competitor, and how it is like regarding to the branding. So these are the things that we would like during the person is taking the morning coffee receive in order to be able to make informed decision. And example of that is that, for instance, Securitas looking for finding out new instances of vandalism and breaking it in. And then, for instance, Sanofi uses meltwater to be alerted when certain patent will expire in target markets, and so on. How the product looks like. So you see, like the person sets up the search, interested search items, and like getting the related news and the changes in the news and the trending things, the media exposure, and also getting daily updates. Then also there are some insights. These are like some tests that I just put them together. So looking at the sentiment, and like for instance here you see Pandora and Google Play and Beats Music and Spotify compared together. And yeah, I always like to talk about also our tech team, because I really like our team, and it's a quite widespread team over the world. And yeah, this is the Stockholm team that is working on data enrichment specifically, but the engineering, of course, is not just limited to the data enrichment. So we work with post news articles and social articles, and we crawl the data on a daily basis, and we have a huge pool of data in the past 10, 12 years. And we provide data enrichments for more than 12 languages, and including sentiment analysis, detecting similar documents, detecting near duplicates, finding name entities, identifying, like summarizing the text, and so on. And using those data enrichments, we are trying to basically provide those insights to make these informed decisions happen. And why we are interested in the deep learning? Okay, deep learning meetup. One is that, well, we are sort of neighboring meetup. So we are organizing the Stockholm NLP meetup, and we had already, Rolof already presented once about deep learning there. And I think they are tightly connected, and it's also very interesting to see, you know, the algorithms that are using the NLP, how they are also used in other fields to get some ideas of how to use them in the specific domains that we are working on. Some examples of why specifically in NLP we think of deep learning. Usually the customer is looking at the, like they have a storyline in their mind, and but they can't really, you know, express it. And then like the people try, you know, pull out their hair and try to make that search happen as close as what they want to say. So one example is that which search term would express data story? What are related articles? How, and if this article is saying something good about that company, so how is the sentiment toward that competitor? And what are the similar articles that the customer would probably be interested in? There are already some publications related to these things in the deep learning, and we in Meltwater are looking at them. And I would like to be here and hear from our great speakers about that. Rolof, I think I'm done.
Yes, so what we all have been waiting for, the talks. So let me introduce Stefan Karlström from KTH.
Okay, thank you very much. So I am actually the head of the computer vision group at KTH. Rolf talked about the computer vision active perception lab, which is actually a bigger thing, which is mainly about robotics actually, and headed by the Lisa Craig. And this group that I've been working on, we have been working in computer vision since early 1980s, basically. So that's it's a very long story. And we are very happy to see that the whole computer vision problem is actually being solved, more or less. I will try to tell you about that. And it's sort of satisfying, sort of when you come to the end after all these years. So, but let me come back to that. So I will talk about deep learning in a very simple way. Okay, nothing really complicated mathematics, very simple math basically. And so I hope you will be able to follow it. And I will mainly talk about what I know, that is computer vision. I will also, but I will mention basically this, because computer vision was the area where deep learning actually sort of made a breakthrough and was very visible. But there has been other areas where deep learning has made interesting progress actually. It's amazing. The areas are almost totally unrelated, and that is sort of the real, you could say, the whole riddle about deep learning, and why does it work so well in so different fields, basically. Okay, but let me take it from the start. You have data, and you can label this data, basically. That is what that is machine learning. This is the general machine learning problem. You think there is a relation between the data and the label. Okay, this could be sort of anything. I mean, you measure you measure the temperature in the body, and why is how you feel, basically, or something like that. There's some kind of relationship. Very often we try to make this relation very simple, so you can have a sort of linear relation, for instance. That's the easiest thing. So basically what you do is, your problem is to find sort of this, what we call the model, the A and B in the linear expression, AX plus B, okay? That is what we want to do. And in general, if you find that, you can sort of plot all the given X, you can compute to Y, and that is what learning is all about, okay? So how do you do that? Well, in general, you might not have this exact relation, of course. So this model could be just an approximation of the real model. Okay? That is the most general case, in fact. Okay. So the first problem is how do you find your model? That is the first problem in machine learning. Yeah, that is how do you find the parameters of your model given the data? Well, since the data is not perfect, the best thing you can do is to try to find the A and B that makes this relation as perfect as possible. So try to fit this linear expression as well as possible to the given data. That is what you try to do. So you end up solving what's known as an optimization problem. Okay? So that's what you always do. So deep learning or machine learning is all about formulating some kind of cost function and solving that using some standard optimization tricks. Okay? And that's especially what deep learning is about. Okay? And in this case, when you have simple expressions like this, you have a very nice optimization problem because you have only one local minimum. Okay? You can, in general, when you have optimization problems, you will have several. Of lots of local minimum things like that. But the beautiful have access. You only have access to a limited set of data, which is known as training data. Okay, and in this case, what you need at least 2 points in order to be able to find the A and B. But in general, you use more than 2 points. You use more points than you need, basically, in order to get an return problem. So then this is. So you only use the training data, in this case, X1 and X2, you find the A and B, and then you can sort of map any new X to the label Y. And that is then you have done machine learning. Okay, this is of course nothing but least squares regression, what you should have been probably doing in high school. I don't remember. So, in general, you can say that the machine learning problem is this: you have a data set to be classified. Okay, you select a subset of that data set to use it for training. You label that subset with the value that is associated with each of these values in the training set. Okay, and this is often the very difficult part. Okay, this is, I mean, having lots of data is in general not a problem. Okay, the problem is getting the labels, because obviously, if it's not a simple problem like this, if it's a more complex problem, it needs some kind of intelligence. This is where humans come in. Okay, this is where you need. I will talk about that in the set when we're talking about classifying images. Okay, and then once you have your labeled training subset, you find your model parameters by solving some kind of cost function. Okay, that works by using all the training data. That is what you do. Okay, so I just noticed I don't have a picture here. That's why I'm looking at this. I wonder why I was looking there. Okay. Okay. It could be a little slightly more complicated. Now I talked about x and y as just scalar values. Okay. The x could actually be more complex, more like a vector. Lots of values for each item is a describable vector. This is a case of, for instance, a digital picture where all the pixels are is here a pixel 1, pixel 2, pixel up to pixel whatever 1 million. So these could be large vectors. Okay, that we can classify. But the linear classifier still works like you have some kind of linear combination, coefficients W, etc. And then you can actually introduce something very interesting here, a nonlinearity. You can introduce a function like this that sort of cuts off. It's linear, sort of linear in this range, and then it sort of gets saturated at a certain value. These functions are very interesting. They're very useful. Okay, because if you use that, if your vector is two-dimensional, okay, you can sort of, and you have two kind of classes. You have the red class and the blue class, okay, and if they are sort of totally distinct, you can actually try to fit a line that separates these two classes. And what you do is you could say that you find a function like this, okay, that sort of outputs with this output. So this is, in this range, the I star is sort of equal to 1. In this range, the I star is equal to -1. In this is sort of between -1 and 1. Okay? But the problem is the same. The problem you have to solve is actually the same problem. You try to find the W1, W2, W3 that minimizes the difference between the y, the given y, and that linear expression squared. Okay, you formulate the cost function in exactly the same way as when you did the linear regression problem. Okay, and you in general come up with the correct values. Okay? So unfortunately, the situation is not always this simple, because it could happen that there is no line that separates clearly the two classes. So what do you do then? Well, you have to find some kind of nonlinear classifier. Then you have to go higher up, more complex function than the linear functions. Okay. Now it starts to get difficult, because nonlinear functions could be anything. Okay? This is the problem. And if you're allowed to have any function, then of course you can sort of fit anything. You can sort of separate almost any classes that are even mixed together, because this is known as the overfitting problem. So here it's not good to have lots of classifiers to choose between. Okay. Okay. But there's another way of looking. If you look at this nonlinear problem, so you could see that finding a nonlinear classifier that separates the classes. There's another way of looking at it. And now we are actually getting right into the deep learning activities. Because let's say that instead of using the values x1 and x2 for solving this classification problem, you use some kind of value y1 that is a function of x1 and y2. And y1 has the property that it is constant on these lines, okay? It is constant on these lines. Y1 is constant. And y2 is another function of the x1 and x2. But it's constant on these sort of curved lines that are sort of orthogonal to the y1. And now suddenly, if you look at, instead of using x1 and x2, you use y1 and y2. What happens? You sort of do a coordinate transformation. You transform the coordinates. Look at the y1 and y2. They are actually completely separate because the blue examples are all to the right of this y1 equals something value here. So in this new space, by choosing new features, I am able to solve, but by a very simple way, by having you can say there's a linear classifier that separates these classes. So I have two alternatives. I can either try to build a complex nonlinear classifier directly, or I could try to find smarter features that solve and that give me a much easier classification problem. Okay. Actually, it turns out, let's look at this. Because I told you that this thing about nonlinear functions, they can look like just like anything. And of course, you would like these to be simply easily computable. And easily computable is still the linear function. But if you take these linear functions, okay, you take a y1 and a y2 like this. And then you put them through a nonlinearity, you will see that if you have, you can actually find for the same data set, you can have one linear function that sort of separates these data very good, okay? But it does a bad job down here, okay? Then you take the second linear function. It does a good job down here, separates the data, but does a bad job up here, okay? Now, if you run these y1 and y2 through nonlinearity like this, you get y star 1, y star 2. And then you make another linear combination, okay? You get the y, and you run that y through this same thing here. You will find that the y value is actually constant along a curved line that sort of ideally separates the two. So this is just a way of, this is a very smart and efficient way of designing nonlinear classifiers. Okay? And this is exactly what is done. It was known as the hierarchical net, especially the convolutional net that I will show you. Okay? So, yes, you might have another way of sort of expressing this is if you start with the x1 and x2, you formulate y1 like this. You can say that y1 is a linear combination of x1 and x2, y2 is a linear combination of x, another linear combination of x1 and x2. Okay? And then you have y star as a linear combination of y star 1 and y star 2. So these represent, these circles, nodes, they represent linear combinations plus this nonlinearity. And now we are talking about sort of these networks, okay, that you might have heard about. Okay. This is the beginning. So this simple nonlinear classifier is a simple network like this, okay? Hierarchical network. Okay. So, and what they do is essentially just, they find, there are very smart way of finding sort of classifiers for these not linearly separable classes. Okay, now, as I told you, there were two ways, as I showed you two ways of actually solving this problem. The first problem was this. You take your data or find some features from this data, and then in general, you end up with a problem of finding a nonlinear classifier. Actually, you might not even be able to find a classifier that separates the classes at all. That is the real bottleneck of these systems. That is the traditional learning, and this is the traditional way of approaching the problem. And there were reasons for doing that. Because I will come back to that when we talk about images. Okay? But you spend, you sort of, what's known as, you try to design features for your problem that you think will be able to separate your classes, okay? And then you spend all your energy trying to design a nonlinear class. That is what people were trying, for instance, in computer vision up until, let's say, 2012. Okay? There was lots of work going on. People had almost decided on what kind of features to use. Everything was about classifying. Deep learning. You learn the parameters. As you saw, the same thing, you could do exactly the same thing by learning the parameters of this hierarchical network, okay? You learn the W's here. And that will give you the same thing. But here you start with the raw data. You start with the X1 and X2, okay? So you learn everything from raw data up until the final classifier. There is no way of saying that. You could say that, okay, you do a linear transformation here. You do a transformation, you have new features, Y1 and Y2, and then you have a linear classifier for those, okay? That's another way of expressing it. But there is no way of, in deep learning, you don't have to talk about feature extraction or classification. It's all the same process. It's a gradual process from feature extraction up until classification. And that is sort of what's new with deep learning compared to traditional machine learning. You learn everything. You learn sort of everything from the raw data. Okay? You don't try to be smart and choose a representation using your own head or some empirical evidence or anything like that. You let the computer take care of everything, from the raw data all the way to the classification. Okay. So, as I said, deep learning makes no distinction between feature selection and classifying. That is the big deal with deep learning. Okay. I will come back to this when it comes. So, of course, these convolutional nets, in general, they are even more complex than just two variables. You have an arbitrary number, long vectors like this. In this case, it's 6 components. You typically have first a layer like this that does linear summation. And then you have another layer that does linear summation of these outputs. And then typically you have a final layer that does linear summation of everything. They are called fully connected layers. These are known as convolutional, because what you do here, convolution because the linear combination of this one on X2 and X3 is the same as the linear combination, sorry, this one on X2 and X4 is the same as this one on X3 and X5. So it's sort of the same linear combination just moving around over the database. That's known as a convolution. And you have to do this several layers. And of course, in each of these layers, you have this non-linearity. Because otherwise, if you just had linear combinations of linear combination, you would always get a linear function at the end. But these non-linearities guarantee that you will sort of get non-linear functions up on the X. So this is typically what these convolutional nets look like. And of course, now I will talk about image classification. In image classification, we will use that. The input here will be all the digital pixel values of images. Typically, you will take an image like this, maybe 100 by 100. It means that you have 100,000 X values, basically. You put these into a vector. And in image classification, there are basically, we have to start with the problem. What we want to do in image classification, we want to take an image like this. And then we want the computer to tell us, what is this? This is a fox, this is a, I don't know, I think it's a cake or something like that. This is a frog. This is something else. Like a baked potato. It's a baked potato? Yeah. Okay, it looks like a cake. Okay. It's the perspective. You see, it's not easy. Yeah. So the first thing you have to do, of course, then, as we saw in the beginning, you have to get your training set. Okay, and getting all these images is no problem. They are all around the internet. Okay, you can just download them. That's not the problem. The problem is to get the content of the image. And to be honest, this is one of the big reasons why there was this breakthrough in deep learning. Because there was a woman at Stanford, female computer vision professor called Fei Li. She got the idea that, okay, now we have this crowdsourcing idea that where you sort of tell people, you pay people to do simple things with computers. And basically what she did, she started telling people you get, I don't remember how much it was, $50 or something like that, for every image that you put your layer, tell me what it is, basically. So now she has built up a set of, I think it's 13 million images that have a label on them in terms of content. And that is one of the big reasons why deep learning was successful. Okay. And here is what her database looks like. You can see upper left horseshoe, African elephant. These are a little dizzy, at least from my point of view. Okay. But it's sort of, I think there are some, I don't remember exactly how many classes, but when you train the convolutional net with these, it's about 1,000 classes that are being used. Actually.
Is it free to use?
Pardon?
This
is free. This is all free. Yeah, that's very important. This is university academic. But you see that they are sort of not at all similar. You know, oh, these are very dizzy. Okay. They can be very, very, very different as images. Okay. Now, and then of course the convolutional nets that you train with these are far more complex than the one I showed you. It turns out that what she does when she trains these convolutional nets, she uses 1.2 million images of 1,000 classes. That is basically around 1,000 images for each class. Okay, for training. Okay. And then she has convolutional layers. I think the first two, these are of course developing every year. So the first had, I think, 3 or 4 convolutional layers, and there was several. Each layer had several sort of possible convolution kernels, and then at the end you had what's known as fully connected layer, where you take linear combinations of whatever is in the activity of these nodes, and then you have a final output layer. And basically the idea is this: if you show a dog image here, you should have this time illuminating, sort of 1 here and 0 everywhere else. If you have a cat, you have a 0 on the dog, you have a 1 on the cat node, and 0s everywhere. This is how you sort of label your output. And then you try to find around 60 million parameters, not 2 parameters. You do a least squares or cost function minimization over 60 million parameters. And this is why it takes computers about 2 or 3 weeks to actually train these nets. Okay? At least it did 2 years ago. I don't remember. I think it's faster. But that is the big one. Okay. So what you end up with after showing each image, you update the parameters, you have your optimization function, and basically then you probably have to iterate and run through the images once more, and eventually you converge to some kind of parameter values on these weight functions. Okay. Yeah, actually, it turns out this is the real structure of the net that we used back in 2012. So you can see that here are like, at this layer, it's there are 13 times 30. It's just a 13 spatial grid, but there are 192 different sort of layers in different convolutions in that layer. That's it. Same thing here. Same thing here. Here's 128 different convolutions. Okay. So here, this is what it looks like what it looked like in 2012. I will show you what it looks like today. Yeah, today. And that was, so they were using some 1, 2, 3, 4 convolutional layers and 2 final output layers. The last ones, 2 years later, people are using 24 layers of modules, where each module has 6 separate convolutional layers. So it's sort of hierarchies on hierarchies here, basically. They are getting far more complex. Okay? But the funny thing about these things is, of course, that compared to, if you go back to before 2012, before deep learning, how did we approach this problem? Well, as I said, we try to design, so we try to be smart. Let's find the features that that allows us to classify an image. And what characterizes this image? Well, you can see that there is like a body, human body like this. Well, typically, of course, the silhouette of the body is very informative. Okay, and the silhouette is characterized by the fact that you have certain orientation of the edges and things like that. That's how people reason. So what about looking at the window here and look at the orientation of the edges? You could build some kind of histogram vector, local histogram vector of the orientation. And that's what you see here, local histogram vectors of orientation of edges. And then you have histogram 1, 2, 3, up to histogram 10,000. And then you concatenate all these histograms into one huge data vector. And that's what you do, and then you build your nonlinear classifier. That's what people did before. They try to be smart. Yeah, it's sort of a smart idea, because obviously visually we see that. I will tell you why was this wrong. Well, if you look at the situation that people in computer vision, we have these databases where we test our algorithms, okay? And basically, there are these databases with lots of objects, okay? Plant, person, chair, etc. And you can see what is the accuracy of recognizing a plant image. Okay, it was 40% back when we started back in 2007. Then it rose, but then gradually, for each class, you could see that it got sort of quick in the beginning, but that back here, I remember there's something wrong here. This is saturating at very low levels, basically. Okay? We are not getting better at all. It's like here, back in 2011, 2012, people were they were not even trying to be invented. They were just sort of combining various tricks together and managed to get 1 or 2% better every year. Okay? It was a very sort of depressed situation. But then what happened was, of course, that, well, it was actually this thing came in, okay? So people like Jeffrey Hinton, Jan LeCun in Toronto and New York, respectively, they had scaled up their convolutional nets tremendously. And in combination with the fact that Fei-Fei Li at Stanford had actually managed to collect this ImageNet database, okay? So they used this ImageNet, they retrained their upscaled convolutional nets. They have been working on these convolutional nets for 25 years, actually. But the new thing is that they had scaled up. The combination of this huge data set and the scaling did a wonderful job on these problems. So suddenly, what happens is that these curves start to skyrocket. Okay. So basically, the average sort of recognition goes from 35 up to 65. Okay. And for certain problems, actually, there are certain data sets, etc., etc. People are actually claiming almost human visual performance in these things. But this is still not human visual performance. But it's important that these curves have sort of turned around, basically, completely. Okay? And this is what ignited sort of the deep learning trend, actually, in the recent years. Okay? So, yeah. What is going? So the question is, why did this happen? What is going on here? What are these sort of convolutional nets doing that the other classifiers were not doing? Well, nobody really knows. This is the problem. This is a great thing. We have almost solved the problem of vision, but we don't have no idea. We have no good explanation. I think it's the first time it has happened in engineering that, I mean, the engineers solve a problem, but there is no scientific explanation. You know, yeah, the great idea is that first you have science, basic research, and then you do engineering from it. This is totally the way around, basically. The engineers have actually come up with the solutions. And now we have the scientific problem, trying to find out what are these things doing. And you know, there are some people saying, oh, they are probably doing the same thing as the brain. And what, oh great, but we have such an advantage over the brain because we can actually measure, go in and measure at every node here, like sort of neuron. Notice I never measured neuron. We could measure basically the activity everywhere. Yes, yes. And that's exactly what the neuroscientists would like to do. That's what they are trying to do, basically. And you know, I heard about the human brain problem, okay? But their networks are sort of 1,000, 10,000 times even bigger. We can go in and measure the activity everywhere. But how do we find out what a certain neuron is doing by measuring? We have no idea what it means. The only way to find out is, if suppose we want to know, what is it? What is this thing sensitive to? Well, we have to put in an image here and vary that image until we get the maximum output here. And then we get the information. And this is exactly what the neuroscientists are doing when they are finding out what is the image excites a certain neuron in the brain maximum. So we are basically back at the same problem as the neuroscientists did. The fact that we can actually know everything what's going on doesn't mean that we have sort of understood everything. But it seems, of course, this is what, like what you're doing here. These early nodes, they will sort of be mostly sensitive to sort of local edges and things like small features, okay? Very general stuff, okay? While if you go later in the network, you start to get sensitive to something that looks like faces and objects, parts of objects and things like that. And eventually, of course, the output nodes will be sensitive to specific objects because we told them to be that, okay? But that's the only thing we told the network. This output node should be sensitive to cats, this to dogs, etc., etc. That is the only thing we tell them, okay? But otherwise, so we get sort of these hierarchical things. Okay, and yeah, so typically the early nodes, they are sensitive to sort of edges or orientation selected features. And the later nodes, they are typically more sensitive to more complex objects. Look, sort of here you can see it's like parts of faces. Okay, so this is the big, you could say the big success in computer vision, but it's not just computer vision. It turns out that speech recognition, same thing there. Deep learning beats everything, okay? Machine translation, automatic language machine translation. Deep learning methods essentially are the best even there. Sort of deep learning, not exactly the same kind of deep learning that I'm talking about here, but sort of deep learning. Natural language understanding, I don't know of any sort of breakthrough results there yet, but that's a very, very interesting area that people are working on. And also, sorry?
Sentiment.
Okay, yeah. So I will come back to natural language. I will not talk about it, but and then of course bioinformatics, very interesting. For some reason, if you look at these things, these nets, they were designed to actually solve problems of like speech and vision sort of real-time recognition problems. It turns out that bioinformatics problems is not, you don't really have real-time problems. You have lots of data that you want to sort of find relations between, okay? You collect lots of data. It turns out that the deep learning algorithm is very good at analyzing this kind of data. I will come back slightly to this. Okay, so here's an example, for instance, where you have actually language and vision coming together, okay? So if you show this to a human, the human will say, oh, this is a tennis player getting ready to serve the ball. Okay, that's typically what a human will write. It turns out the computer will, by showing the computer lots of these images and lots of captions, of course, together, they can learn both. They can sort of be able to put a caption automatically on images like this. Okay, these are very recent results. They came out, I think, in October, November last year, something like that. You know, there's actually 3 or 4 groups at the same time: Google, Microsoft, Stanford U, and I think Toronto. All at the same time, they published papers on this. And of course, this is probably what you want to do for Google. I mean, they are really interested in this. Okay. Speech recognition, I said. Instead of having pixels, speech signal is just lots of variation of pressure on your ear, basically, and you can sample those and digitize it. So it's lots of numbers, basically, a word. Any sound is just a lot of numbers in sequence. So you can do exactly the same thing. You have to, of course, you have to let the window run over the speech signals. But essentially, you use the same kind of convolutional nets to classify the speech signal. Turns out that the Chinese Baidu company recently put out this, what they call deep speech, which I think this represents sort of the, I think it's the word classification error or something. I'm not really sure what it is, but you see there are quite good improvements compared to standard things from Apple, Bing, Google API, etc. So they beat everything, and that they are doing sort of deep learning. So these are probably the image and the computer vision and the speech is, of course, probably the big success story. But you might also have heard about when you come to natural language, for instance. So this is maybe not natural language. These are, the Watson, the IBM Watson machine. Okay, it's sort of question answering machine essentially. So it's, I don't know if you can say that there's some understanding going on. But it's interesting. They are trying to actually promote this to actually answer questions in healthcare and things like that, being able to basically replace doctors, things like that. And they recently acquired a company called Alchemy API, which is a deep learning specialization company. So they have noticed this thing, of course, that if you want to improve these things, that deep learning is where you should be going. And probably the most interesting stuff that has come out very recently in December, there was a group from Toronto led by Brendan Frey. They found there's something called the splicing code. I shouldn't talk about it because I don't understand exactly what's going on. But obviously, it is when proteins are synthesized, they are synthesized from fragments, and these fragments are put together depending on some kind of DNA code. Okay, if there's a mutation in DNA code, you get an error in these proteins that are put together, basically. And they were able to identify exactly those mutations that give you errors that cause, for instance, cancer and various diseases. Okay? They actually, I think, up until December, people had found about 100 mutations that did this, and they found some 50 more mutations. Okay, that's interesting. And it's sort of basic research in biology using sort of this very much the same deep learning convolutional net algorithms as we did for visual recognition. And this is where it starts to get strange. Why is this algorithm so effective on so different problems? Okay, Another, this came out last week. So multi-task network drug discovery. Basically, you have a set of target molecules, okay, that you know that if you can find some drug that sort of targets this molecule and silences it will be an effective drug or something. And of course, they have lots of data that these drugs, they are effective so and so on these targets, but they have very scattered data. But by putting all these data into a neural network, they were able to actually discover even more drugs, more interaction between drugs and targets that were totally unknown. So this is another success story. Exactly, Google is involved. Same thing there. Why should this work? Also, it's totally unrelated problem to vision and speech, like where convolutional nets were actually designed, but they are actually using these things for solving this problem. Okay, so, and that is the big question. It seems that deep learning is some kind of generic tool for actually finding these mappings where you have input into a complex system and you get some output. Okay. And this complex system could be seen almost anything. But in general, of course, in terms of image, like computer vision is human knowledge, okay? You have to put a human there. And the human decides the output. Okay? So you're trying to replicate sort of human knowledge. Okay? That is what you're trying to do. And of course, here we come. The big thing about is of course, the big data input to human knowledge is, of course, language. That is, and the big output from human knowledge and language is, of course, understanding what language is all about. Okay? So here is what is really believed in general, where the deep learning will take off. This is the next takeoff area for deep learning. That's generally believed. And of course, Rolf can tell you about these things. I hope you will probably come back to these things. I shall not do. And as I said, the real maybe interesting things from a sort of society point of view is of course this thing. You can replace human knowledge. And for instance, a medical doctor. Okay, what does a medical doctor? Well, a medical doctor looks at the tests in the lab that he comes back, your blood, whatever. You can he listens to your body, but you can also go around and wear whatever things that register the signals of your body. And these are becoming more and more common. You know, everyone can buy these things more and more. He can talk to the patients, and of course, eventually we will also have everyone will be able to produce his personal genome, okay? Combining all these things. And then you have the output medical state here. Okay? This is what you would really like to do. You would like to map all these measurements into the health state. And this is essentially what you do. And it's sort of, you could say that, yes, this is an example of sort of, we are talking about professions disappearing, and we in general think about, oh, manual labor. Well, now we're talking about not really manual labor, now we're talking about intellectual labor. It's probably not disappearing, but of course it will change. Because what you can do with these things, you can produce a medical expert that sort of uses information, not from just his own expertise, but all the medical doctors in the world. And doesn't mean that you will get better predictions anyway. You shouldn't hope too much with that. It's not like we are trying to build some super intelligence, basically. I think we are just sort of reducing the errors here. That's what we do. But it's interesting. So all these sort of, yes, almost purely intellectual professions will be faced with this. I mean, journalism, for instance. I mean, you have seen these things like small texts are being written automatically, more or less. The journalist takes in information, it outputs text. Okay, you could train these things to do that. I don't know, lawyers, for instance. I mean, anyone, basically any human decision that uses information makes a decision. If you just have access to these decisions, then you can train your network to do the same. So that brings us to, okay, what we have seen here is that the deep learning is a powerful way to find mappings between raw input data and labeled output data. When we say labeled output data, in general means that you need some kind of intelligent agent to tell you these levels. And these mappings, they generalize outside these sets that you use for training. So it can actually predict new unseen raw input, okay? That is totally unlabeled. It can put a label on a new raw input. That is what it's doing. And it turns out that it works over images, speech, and also on genetic data, whatever. Whenever you have data into a complex system, you have some well-defined output that you can actually register. That seems to be the only thing that we need. Okay, very different domains of application. And of course, with these data sets, that is now what you need. That is what you are using now. It's not the software. Everyone will have access to the software. So it's basically, the competitive edge here is basically data. That's what gets your head. That's the important. That's why everyone is talking about big data. But this is sort of this is sort of the science between the people. Okay, thank you very much.
We're a bit behind on our schedule, but if there is some questions for Stefan, now we have Stefan here. We can take some minutes, maybe to explain about some of the applications or some other. So go ahead.
Yeah.
So, are there any guidelines on how to choose these convoluted networks to solve different problems? Because so far you just said we take them for granted. How do we choose them?
No, I mean, you just, well, the guideline right now seems to be you make them as big as possible. that was what happened in September last year. I mean, up until then, everybody had used 4 or 5 layers, and then suddenly everybody comes out with 18, 20 layers. Okay? I don't know. That's the only guideline I give you. Make them big. And that's the fascinating thing about this whole thing. The fact that by scaling things up, you make them work better. I mean, as I said, people have been working on these for 25 years. And they tried, and they were using just single layers or maybe 2 layers or something like that. They tried these things on these vision problems, but they were beaten by the computer vision people. But then they scaled everything up, made it more complex. And the general experience as an engineer, when you scale things up, you don't solve problems, you get problems. But here, exactly the opposite. You solve problems by making a system more complex. You get the simple system, the better system. And I don't think they understand it themselves. Okay, well, you had one that.
We used the microphone, so it's recorded as well.
So you didn't mention anything about regularization of parameters. Is that because there is no regularization, or is that because you didn't go into that?
It's an interesting topic. Basically, you could say that the regularization is sort of built into the structure, very simple convolutional structures, sort of. The whole idea with regularization, in my opinion, is this, that you should put constraints on your models that reflect the structure of your data. And it seems that this exactly is why these things work, that these convolutional nets, hierarchical convolutional nets, in some sense, the structure that you get there reflects sort of the structure of the data in the sense that at the low level, visual images are very similar. so they have edges and things like that. Okay, so you are sharing the same features over several classes. That is basically a dog, a cat, a car, whatever. Besides these lower nodes, exactly the same thing. But then as you get higher and higher, you get more specialized. I think it's that sort of process of going from very general feature sharing down up to specialization. That is where the regularization is taking place, because there is some regularization built into this called dropout and things like that. But that's not the crucial thing, basically. I think the crucial thing is the fact that this structure of the nets reflects the structure of the data in some way. But why is it then so generic? Why does it work everywhere? I don't know. There seems to be something very generic about large data sets. Whenever you have large sets of data that map in a structured way to outputs, okay, then you have these kinds of regularizations are the natural way. I don't know. That's the only answer I can get.
Thank you.
Okay, we can take one last one.
Okay, my question is, what is your opinion about the images, the special tailored images that are made to fool any deep neural network?
Yeah, there are two kinds, I think. The one that you can build a recognizer for a cat, and then you can put in almost random noise, and it still says cat. Okay, and that is because basically the space of images is very large, and I think these classifiers they focus on the examples that you give them, and they turn out all the good cats, but they turn out a lot of things that in practice it doesn't matter, because look, I don't know how to put it. It's not like if you take a random image, you have to try out. I think you have to optimize for these random images, and you know, to get the cat response. Okay, that's what you have. And in general, it's no problem. In practice, it's no problem, because these images seldom appear. Okay?
But a related question,
Yeah.
Because these networks have 60 million parameters.
Yes.
To recognize 1.2 million images.
Yes.
So, do you see a...
Yeah, but each image has about 100,000 pixels.
Yeah.
So it's in terms of dimensionality, I don't.
But still, I mean that.
You think we are?
No, but the images that are special made not to be recognized,
yeah,
or like they maximize the errors. Let's say.
Yeah.
To a human, they would appear just. Noise.
Yeah. I mean, these are not doing what humans are doing. Something else. There's something going. I haven't spoken about human vision. Know that. These things are doing something. This is engineering. Okay? So human vision, forget about it. This is not doing human vision. This is doing something strange that we don't understand. But it turns out that this problem in practice has not turned out to be a problem, because you have to. They are so rare, these images. You really have to look for them, basically. That's the thing.
You think the image stands?
I'm thinking about bioinformatics and these things.
Okay.
Yeah.
Yeah. You mean okay? Yeah, sure.
There's a lot of questions I can see, but we can take it in the break or during the mingling.
We will try to have still the mingling time in the end. It will not be an hour; it will be less. But yeah, do grab Stefan. I think you're also sticking around a bit longer. So then now we move on to the break. So thanks, Stefan, for your great presentation.
So we'll have, maybe we keep it short, 10 minutes break. How long? 10 minutes, maybe?
Should we make it just with the mics when there are questions?
When people are asking questions, yeah. Okay. I think here it's possible to hear it because it's recorded and standing here, it's fine.
We also have a mic for the speaker, so basically it's a handset.
Yeah.
Do you want to?
Yeah. Do you want the microphone?
So we're not going to use the headset?
No.
Okay.
For now.
Okay.
Nice work, man.
Yeah.
Yeah. Happy round.
Okay. See you.
Then we're gonna make it. Everybody who wants has a question.
Yeah.
Raise her hand up.
Yeah.
I'm gonna go with the mic, and then she is gonna put the question.
Yeah.
Because this is kind of like going to be, half of the question is going to be without the mic, and then with the mic, it's not a problem. But if you're recording it, it's going to be
That's why
unprofessional if you're going to use the. Exactly. Yeah. It's perfect. I'll be here in the
I will ask. Yeah.
Do you want me to announce it or? Well, maybe you gather the crowd.
Okay, we're going to start again. Sorry, I'm going to steal some time from the break. So, are we all ready for another exciting adventure with deep learning? So, meanwhile, I'll introduce Josephine Sullivan. Josephine works at the same lab as Stefan Carlson, also in computer vision, and has been working, I think, also a couple of years, 2 years or more already with deep learning. So I give the floor to her.
All right. Your moment to sit down. All right, so this is quite exciting. This is generally more people that come to my lectures. Okay, so I'm going to retread basically the same path as Stefan, but I will get more into the nitty-gritty details. But we'll have a gentle introduction at the beginning so that we can build up a head of steam before we get to the more, let's call it, fun parts of the talk. Okay, so what has deep learning done for computer vision? And I'll just reiterate what Stefan did in his last talk. It's resulted in much better visual image classification and object recognition or detection, and much more powerful generic image representations. Okay, so this is what Stefan's talking about. Okay? But what I should really say, what deep learning that's really a decade ago, or say from 2006, Jeff Hinton and all these people were on about unsupervised methods for doing deep learning. But because they're so computationally inefficient, you cannot train them on large amounts of data, you cannot train very deep networks, you can't get the same performance at all on computer vision data sets. So this is why they were going nowhere, or appeared to be going nowhere. until CovNets entered the scene again, and they were scaled up to have very many layers, and they were trained on millions of images. Okay. Okay, so let's just try and convince you and give you some numbers to say how well they revolutionized the division. So this data set that Stefan was talking about, the ImageNet data set, so it has a competition. So it has 1.2 million images, 1.1 or 1 million are used for training, let's say 100,000 are used for a validation set, and then there's another 100,000 for a test set. And then when you train your algorithm, your classifier, you get to have 5 guesses about what the label is for this image. You get 5 guesses because usually there's more than one object in the image, but there's only one label. So this gives you a chance to get the right one. So here if you output scale, t-shirt, steel, drum, drumstick, wood turtle, because the 2 label is in there, you get +1, and if you don't get the ground truth label in here, it's a wrong answer. So then your error rate is just to sum up all the images where you got the wrong answer and then you divide by 100,000. Okay. Okay, so this was the error rate in 2010, the 8.2%, error rate in 2011, and then there's a big jump by almost 10%, or say 9%, and this is with the introduction of a deep convolutional neural network, or convolutional network. Okay, and then there's been steady progress since then, but on a high conceptual level, there's no difference between this network here, that one here, and the one that worked in this, that one in this here. It's just, it's deeper. Okay, but it's more or less exactly the same, just scaled up. Okay. And then the graph that Stefan was talking about, object detection. So that was image classification. So that's where you input the whole image and you say whether there's a person in there or there's a steel drum. There's a harder problem, which is where you want to put a bounding box around the object that you detect in the image. So you may say, is there a person in this image, and where is the person, and you put the bounding box around. So this is sort of considered a harder problem because you have to localize the object within the image as well. Okay, so this is where we have the second graph here. There was saturation with the old school methods of solving this problem up until 2011. And a bit beyond as well, because the news of the great results in image classification didn't filter through into all the systems that perform object detection until the latter half of 2013. Okay, and this is where we start to have, in the last year, all the hardcore coders who have their complicated systems for doing object detection put in the deep learning, the CovNets representations and machinery into their systems, and they doubled the, in basically 1 year or 1.5 years, they doubled the weights on these data sets. Okay? So this is very exciting because at the original 2012 meeting where this AlexNet got very good performance on the ImageNet database, people were like, oh, but that's just image classification, that's no big deal. The real challenge is object detection. So I think when it starts working here, this is where people started entering the CovNet boat and saying there's something really important happening here. Okay. And then there's the work that we've done in our lab, which is if you train a deep CovNet on ImageNet, and then you just take the responses from one of the latent layers, this actually builds a very good image representation. And if you just learn standard SVN linear classifiers on top of that, to solve lots of different image recognition, visual recognition tasks, then you can get actually very good performance. So here, the red is what I've just described. This is what we did. So this is about maybe a month and a half work to get each of these red lines, or these red bars, and we compared them to the state of the art at the time in March 2013. To the state-of-the-art method for that particular data set or that task. So just think that each of these blue bars could be many years of work, and it's a whole lab working on this problem. We replicated the numbers on these different data sets that range from object classification, scene classification, to instance retrieval, which is I have a picture of the Eiffel Tower, you know, find all the other pictures of the Eiffel Tower on my database. It doesn't actually, it works more like I have a picture, tell me where it is from, and then you search, you look for similarities between that picture and all the pictures in your database that have a label, and then you just transfer the label from the closest image in your database. Okay, so this was actually technically the very simplest paper we've ever written, but maybe the most important. So this is, and people got very excited about this because it was like, oh, okay. People got, you know, you could either get depressed by this because this negated decades worth of research within a couple of months, but it's probably much better to embrace it and get very excited. So this is where I have to say Stefan is maybe somewhat unusual. He's been around a long time, but he's more excited about this than bitter. Okay, so that's very noble of a true scientist. Okay, so what was the reason for the jump in performance? Okay, so now we're just going to go back to what type you solve computer vision. And this is what I teach my students in the computer vision course. You know, in a modern visual recognition system, you gather your label training data sets, you extract a feature representation, and then you construct a decision boundary between, let's just consider that we have a binary classification. You just construct a decision boundary between the two classes. And then at the test phase, you extract a feature representation, and then you compare it to your learned decision boundary. So this is just supervised learning, and I'm presuming everybody in the room knows about this. So this is just a photo representation of this. Green dots, faces, red dots, motorbikes, and then if you have a new blue dot, is it a face or a motorbike? So you basically compare it to some decision boundary that you've learned using whatever method that you want, whether it's generative, distributive, etc. Okay. So obviously, for a long time, as Stefan was saying, people were fixated on either focusing on building the decision boundary or on building good features. Okay. So obviously, if you just use the RGB pixel data, you'll probably, if you look in that space, this is probably, they'll all be intermingled, and it'll be very hard. You either have to decide on a very complicated decision boundary, or it's not going to work very well at all. And this is the ideal case. If you say you want to do classification, this is ideal. All your faces get mapped to more or less the same volume in your feature space, and all the motor size gets mapped to some other volume, well separated from faces. Okay. So supervised deep learning allows you to learn these ideal features, or it seems to, from the performance that you get, and from the graph that we showed where you could just get the image representation and learn a simple linear classifier to do lots of different tasks that will do, you know, lots of different visual recognition tasks. Okay. So this is just a quick summary. So traditional, the white box here indicates this is some engineer has pulled off some way of doing feature extraction, and then you have some trainable classifier that does the decision, makes the decision for you. Then in modern times, you've come up with some feature extraction, and then you've built some middle-level features. You know, you find some exemplars, you build histograms of these. People heard of bag of word models and things like that. This is what I'm talking about here. So you build bag of word representations for different images, and then using those, then you start training classifiers on these mid-level features. Whereas with deep learning, you have low-level features, then you have mid-level features that are combinations of these low-level features, then you have high-level features that are combinations of mid-level features, which are then attached to a classifier. But each of these is learned in tandem, so you have this end-to-end learning. Okay, so this is the really important thing. So the key properties are, basically, you have a mechanism for learning a very highly nonlinear function. You can learn it from data, and also that you can shunt lots of data through this learning algorithm. Okay, this is really important. And the features that you build, they are hierarchical, and it's a distributed representation, and you can compose all these features together, and there's lots of feature sharing going on. Oh, and also this is another thing about these CovNets, which is great. before it was a real pain in the arse to do multi-class classification. Okay, so either you did, oh, I build one SVM, one against the rest, or one versus one, and whereas in the CovNets, because you do so much feature sharing, you extract all the features from an image, and then you you look for all of the objects all at the same time. So this is the very nice appealing thing. So they may be slow to find one task, but if you're looking for 1,000 tasks or 10,000 tasks, it's an extremely efficient way of doing it. Okay? And also the other important thing is that you do end-to-end. So you do the input is the raw RGB, the output are the class labels, and then you learn everything in between. Okay, so how? So what are convolutional nets? So maybe I skipped this, just saying that they're everywhere at the moment. They're very good. Image recognition, speech recognition. If you go to Kaggle now, a year ago or 3 years ago, everybody was random foresting or ensembles of forests. Whether they were learned in a boosting, etc. It's like me now. I supervised lots of extra pieces or master pieces. Every single one in industrial used to be a random forest, and now everybody's doing it. So I'm wondering what will it be in 5 years' time. But anyway, they are applicable. You use them for array data where nearby data points are correlated. So this is where they work very well at the moment. Okay, so as Stefan alluded to, these things have actually been around for a very long time. So we all have to say, God bless Jan McCutcheon, he developed these in the 80s, and he was at Bell Labs, built lots of things like digit recognizers, face detectors. But he got a hard time publishing a lot of the work, but he kept stuck to his guns. And now he's head of AI research in Facebook, and I presume it wasn't going to be that. So, okay. But the main thing to say is that the training is supervised, and you train it with stochastic gradient descent. I don't know if that means anything to anybody. Okay, okay, a good portion. Okay, so this is just the history. So, they originally in the 1980s, then Jan McCutcheon came up with basically a way of training them. So this was the backpropagation of basically stochastic gradient descent. Then in the early aughts, basically people were obsessed with unsupervised feature learning. But then Jeffrey Hinton in 2012 said, okay, I'm just going to try and solve a problem with a big massive CovNet, and I have lots of data to train it. And that sparked the interest, and lots of people working on this more recently. So you can see this, we've just been, like a pendulum spiraling back and forth, revisiting CovNets as the tools that we have and the data that we have changes, and saying, oh, well, maybe they're more useful now. Oh, maybe they're more useful now. Oh, maybe we have a chance to try them again. Okay, so but the reason for the breakthrough now is basically we have access to large stores of labeled data. We have GPUs. That means that we can do many, many, many iterations of backpropagation or this stochastic gradient descent, which would have never been possible before. And also, the networks have been made deeper, and that seems to be a really, really crucial part of the whole process. Okay, so this is the AlexNet. So this is just showing that we have 1, 2, 3, 4, 5 convolutional layers, 2 fully connected layers, and then an output layer here. Okay, so this just gives you a scale, the size of the scale. Okay, so what are the basic operations that you do in a convolutional neural network? So the main operation is the convolutional operation. So let's assume that we have a set of 2D feature maps. So if this is the input image, one feature map is the red channel, the second feature map is the blue channel, third one is green. I've gone the wrong way. Oh, you understand what I mean? And each channel is 2D and is size, let's see, big W times big W. Okay. Then we have the convolution. If we have one convolutional kernel, that basically means we have a set of 2D kernels, K, so K1, Kn, and each Ki is also 2-dimensional, but it's only like a small little thing. So this is 2W, it's 2 small w plus 1. So it might be a 3 by 3 filter or a 5 by 5 filter. The biggest I've seen is maybe 11 by 11. Okay, and then you have some values. Big. Okay, so how do we put these together? So basically we define, so I'm going to call this convolutional operator here, and it takes as input my set of feature maps, my set of convolutional filters, my bias term, and basically I do a 2D convolution between the Ki, I convolve that with one fixed map Xi, and then I do each of the M convolutions, and then I sum them all up. Okay. And then I add my bias. So I'm using this symbol to represent convolution. Who remembers convolution? No, if they're all engineers, if you don't know what a convolutional is, it's basically you say I have an image here, and then this is my filter here, my patch, and each of these has a weight here. And the pixels of my image section under the filter, I just multiply my image here with this number here, the weight here, this pixel value here with this weight here, etc. And then I do these I do a dot product, and then I sum them together. And basically, I then move this filter all across my image, and for each position point where I stick down my filter, I get a response. Okay, so these things people used to. I mean, if people have used Photoshop or any image manipulation tool, if you use something that looks for edges or there's blurring, normally they have there's some filter here that gives you this effect. So whether if you blur this, all these weight values maybe correspond to 1/9, so you give an average filter. Okay. So this is what's going on here. Okay, so back to here. So this is what I tried to show here. This is a small little 3 by 3 filter, or a 5 by 5 filter, and it has 3 maps. Okay, so this is what's going on. So you could see this basically as a 3D convolution, but you only move it around in the XY direction, not depth, because it's the same size as the number of response maps that you have. Okay. Okay, so then after you do your convolution, so then when you do your convolutions for one kernel, you come out with a 2D response map. Okay, and then you put every single number in this response map through a nonlinear function, which is called the sigma. And then one of the important things with the new convnet is that this nonlinearity is something that's called ReLU, and it's just basically if your response is less than 0, you replace it with a 0, and otherwise you leave it. Okay? Whereas before you used to have something called sigmoids that looked like this, so they would actually saturate if you had a very big number or a very small number. Okay? So this was, this is actually quite important for the optimization process, okay? Because it means when you get the wrong answer, you get a very large value in your error function, and it means that you move much more quickly to try and correct it. Whereas when you saturated, there was no difference between getting a really wrong answer and a bad answer. So you move much more slowly. Okay, and then after you apply your nonlinearity, you have a pool operation. And what basically that means is that you divide your response map here into lots of small patches. They could be overlapping, they're not overlapping in this, but in each small subpatch, you take the maximum value. Okay, you just replace, say this is a 4 by 4 or 5 by 5 neighborhood, you just replace that 5 by 5 neighborhood by its maximum value in that neighborhood. Okay. So why you do this is because you reduce the size of your map, but also it gives you some invariance to rotations and small geometric transformations. Okay. Okay, so basically that's the 3 operations that you do in your convolutional part of your convnet. Okay, and basically you just build on top of these. So at convolutional layer L, you have a set of ML feature maps. You then have multiple sets of kernels, so I've added this extra subset j to know that instead of applying just one set of kernels, you apply multiple sets of kernels. And for one set of kernels, you do a convolution, you do your nonlinear activation, and then you do your pooling operation, and you get a new response map. Okay. So this is what this is just showing here. So this bar here for your kernel, this is one set of, so this equals 1j, okay? And then you get this response map here, and then when you do pooling, this is the final response map that you get. And why this is extended is because you have n L squared of these different kernels that you apply. Okay, so hopefully makes sense. Okay. All right. So then this is your AlexNet here. So these are all the convolutional layers here. So I've made these dotted because here they do the pooling operation or the subsampling operation. And there's a solid line as opposed to dashed lines. They don't actually do any subsampling here. Okay, so that's just the difference here. Okay, so when I get to here, what do I do next? Okay. So here you have your first fully connected layer. So this is this part of the operation. As you can tell, I have a background in mathematics, so I like having complicated notation. Well, I would say correct notation. Maybe not. But effectively, what you do is, so here you have a 13 by 13 by 128 set of responses. Okay, so here they're shaped as a cube. But what you essentially do then is just, you should reshape this as one big long vector, okay? 1D vector. And then you connect, to get the response here, you connect this to every point in the other vector, okay? So this is what this is basically. Okay? So the important thing, so this is actually where 95% of your parameters are, okay? Because what happens here is you're saying, I'm going to learn. So this is 13 by 13 by 128. And I'm going to dot product this with a W to get the response here. Okay. And then then you have 4,096 responses. So you have to multiply this by 4,096 here. And that's how many different parameters you have to learn at this stage. So this is these W's here. Okay, so this is actually where, where you get the 60 million parameters from. This is where most of them are. Okay, and then at the next convolutional layer, this response here is connected to all the 4,096 here. So you have a weight for each of those lines that you connect here, and then you have 4,096 of those. So there's another big chunk of the parameters are there as well. Okay, so this is just what this is what this is just saying here. Okay, so for each response of the next layer, you have a set of weights here that connects all the x's from the previous layer, all those x's from the previous layer. Okay, and then finally, we want to get, so in ImageNet there are 1,000 classes, so we want our output to have dimensionality 1,000. So this means we go from the last fully connected, the responses from the last fully connected layer, you dot product with these W's, and you get an output. So let's see is the number of classes here. So that means we get 100 numbers. And then to make it easier to interpret and or to pretend that they're probabilities or whatever you want to say, or you want to do a max, you want to find which of these 1,000 gives me the max response. You could do a max, but you want something that's differentiable and nice and smooth, so you do something that's called the soft max. So this operation here is you take the exponential of this O dash, and then you divide it by the weight, or the sum of all the O dashes here, okay? So this is like a max operation, but it's smoother. So this is what you get, okay? And your targets in general are things like 1, 0, 0, 0. And you're aiming to get those with this. You'll never get quite exactly that, but you'll get like 0.988, 1, and then close to 0 for everything else. Okay. Okay, so this is just all the parameters of the model. You have your convolutional layers, so there's lots of different kernels that you have to learn. Then you have all the fully connected parameters from your fully connected layers. The big one which connects the responses from the last convolutional layer to the responses from the first fully connected layer. So this is these parameters here, and then the parameters of the subsequent fully connected layers. Okay. So how do we train this? So now you understand how the function is built up. So it's quite expressive. You can do lots of things, but that's but obviously there's lots of values of this parameters that if you apply it, you won't be doing anything. You won't be recognizing anything but nonsense. Okay. So how do you train this? And this was the amazing thing. Well, to me for a long time was like, I have 60 million parameters. How can I learn? I have to find a good value for these. How do I do it? Okay. And the answer is not surprisingly quite simple. Yeah. So on a high level. Okay, so we do supervised learning. So remember, for my RGB image X, the CovNet's first set of 2D feature maps is just the red channel of this input image, the green channel, and the blue channel. Okay, so they are 3 feature maps. And then you have a set of D of labeled training examples. Okay, so that means you have many input images and their corresponding labels. And then your task is to learn all your parameters of your model, both the convolutional parameters and the whopping big set of fully connected parameters. Okay? And the key here is somehow you must link my parameters with my performance of my network on my set of labeled training. Okay, so this is, you have to set up, this is the optimization problem that Stefan was talking about. So you have to remember the CovNet is just learning a function from image with the combined with some parameters to a 1, 0, 0, okay, to the number of tasks that I have. Let's see. Right. Okay, so basically you have a CovNet, you have an input image, you have your current set of parameters, and you get some prediction of the label. So basically you use a loss function to measure the error that you get in this CovNet function for, you know, the difference between the predicted label and the ground truth label. So you have something called a loss function. And typically, if y is the ground truth label, y hat is my predicted label. If this gets bigger as the distance between these two things gets bigger. Okay? So conceptually, that's so the very simplest loss function that you can have is if y equals y hat, I have 0 loss. If they're not the same thing, I have a loss of 1. Okay, so that's the simplest thing that you can have. But this is actually the loss function that people use for training image classification. Basically, it's something called the cross entropy loss. Okay, so this is this will give you 0 if you have 1. I mean, say the yj's are actually, the ground truth labels are usually just 1s and 0s. Okay, there will be just 1, 1, and everything else will be 0. And then the y hats will be numbers between 0 and 1. I'll let you figure it out for a homework exercise. When y hat j has all the same entry, all its entries are exactly the same as the entries in y, and when they differ, you can figure out. This will basically be 0, and it will be large. You have a minus, because remember the log between 1 and 0 is minus. Okay. Okay, so now we have a way of measuring. I have a CovNet, I have a function that makes a prediction of the labels, and then I have a way of measuring how close that prediction is to the ground truth label. And then you just define this one, call this E. Okay, you have some energy or some cost function. Okay. So then the problem is, easy peasy, how can I move it? How can I find a good set of parameters that the average loss is low? Okay, so easy peasy, especially when this has dimensionality 60 million. But, yeah. Okay, so how do we do the optimization? Okay. Okay, so this is our optimization problem. And all you do to optimize is I randomly initialize my W's. Okay, so I have an initial guess. As long as, and this is the amazing thing, as long as you don't do something very stupid like give everything the same, give all the parameters the same value, or you don't make them too big, you just make them roughly around 0 with some standard deviation. Okay, so there's some random initialization that's not too stupid. Then you just have an iterative process, which we call then you this with respect to my parameters and compute its value at compute the value at the current values of my parameters, and then I update my current estimate of my weights. Okay. And this WT is the learning rate, and this says how much I update my current estimate of the parameters. Okay, so that's what we do there. And then you just iterate this a couple of hundred times. Okay, so this gives you the right ratio between I don't have to put too many samples through my network, and it's going to take ages to do an update step. So if people know about if I find a local minima of this cost function, will I get a network that's able to classify images? So I can see this is a big cliffhanger for you all, but the answer that gives you some intuition about the hardness of training a deep conv net with back propagation. Okay, so up until 2012, and maybe this was actually true when you had networks that had much fewer layers, was that most of the local minima in this cost function were junk. Okay, so if you found a local minima, it was probably not much use to you. Okay, so basically this process of doing a random initialization of your weights, doing stochastic gradient descent to find a local minima was pointless. So I should say that if you would say I initialize my parameters here, stochastic gradient descent allows me to just fall down this valley and find a local minima here. So that's all that stochastic gradient descent does. Okay, and it does it, yeah. Okay, so this was the common wisdom up until 2012, and this is where the whole it was always like there were 3 or 4 groups, and it was like dark art or black magic that they were able to train these networks to do sensible things. You know, even on some images, even you would always be like, oh yeah, there's only Yama Kun and Jeff Hinton and Yoshio Benjo. They're the only people that can train these networks because they know all the tricks and they have lots of experience. If you or me just sat down with the same data and the same algorithms, we'd never be able to train anything. But now, basically everybody, you know, every man with a GPU and a dog can now train these networks, and ImageNet. Basically, it's now the case that we think that the cost function surface looks more like this. There's lots of local minima, and they're all equally good. Okay, and one reason why there's lots of local minima is that I can commute my weights. So imagine this was one network that I learned. If I just commuted the nodes and the weights, it's effectively the same network, but obviously it's a different W. It's somewhere else in my parameter space. Okay, but it's exactly the same. I mean, effectively you're going to have the same performance on the same data. Okay, so basically there are lots of And the thing is, you don't want to miss it, so your learning rate shoot, or you might miss it. Okay, so that's the other important thing. And then the other, this was what I was talking about before. So this ReLU operation that we're using now, instead of these for the activation function, whereas before, should I finish soon? Or, okay. I know that I'm so entertaining. So fascinating. These are very important. I mean, this was what people did before, but this was not good for optimization. Okay, so this slowed down optimization a lot, because as I said before, when you got a very wrong answer on your cost function that looked almost the same as getting quite a less wrong answer. And that means that you didn't learn as fast. Okay, so this is from here. This is so I suppose somebody asked about regularization. The question, they're gone now, okay. It's more a question of how much training data do you need given how big your network is. And I think people are trying to figure that out. And the important thing is that if you have a deeper network, you can get away with having a fewer set of parameters than having a shallower network, but having it very wide. Okay, so having many, many filters, okay, or big filters. So somehow you can trade off depth with width and size of your filters. Okay, so this is the slide that I have about regularization. So it's still a neural network, so there is still a danger that you will overfit, and especially if you're lacking in labeled training data. Okay, so you avoid overfitting by training with lots and lots of labeled training data. So I said that ImageNet has 1.1, let's say you have 1 million images that you train with, but most people augment their data set by artificially jittering their data. So they apply small translations or small rotations. So they effectively train with, say, 10 million images as opposed to, but obviously there's lots of correlations, but okay. You train for a long time with slow learning rates. Maybe you train maybe with a relatively large learning rate, but then after each epoch, so an epoch is when you go through all your training data at once, you reduce your training rate bit by bit. There's dropout, so this is the idea from Jeff Hinton. So you only classify and update a random subset of the network at each training iteration. So this becomes, you have to be more aggressive with this if you have less training data. So dropout becomes less and less important if you have more and more labeled training data. And then of course you have to be vigilant, okay? You have to keep your eye on your performance on the validation set, okay? So do people know what validation is? So hopefully you're all here. If you have validate, so you have to keep an eye on that to make sure that you're not overfitting. Okay, so that's very important. Should I stop there?
No, you saw 5 minutes time.
Oh right, okay. Okay, so this is just going. Maybe I can skip the bits on ImageNet because I should just say, I suppose, that if people, you can download this. This is the small version. There is a large version, but somebody, I think it took them 5 days to download it, and then maybe a day or two to unzip it. So it's a bit of an epic undertaking if you want to go for the big, the 14, 15 million, the size data set. But the one that most people use, 1,000 image classes, 1.4 images. And this is the classification challenge, and then there's also a detection challenge, and then the detection challenge, it's a smaller data set. It's 200 object classes and say 500,000 images where the bounding boxes are labeled. Okay, so this is what it looks like. These are images from ImageNet. So this is a good paper to go and read actually, because it tells you the variation that exists in this data set. Okay. Okay, I'm going to skip this and this and this. This is just an example of the results that you get from the AlexNet on ImageNet here. So this is the output that you get, or this is at least say the top 5 responses that you get. I think the ground truth labeling is the one in pink, and the rest are not so much ground truth. So the really exciting thing about these covenants is that sometimes you may get the wrong answer, or you may get other answers, but they're relatively plausible. Okay? So what happened before in computer vision with these hog and sift or man-made feature descriptors, you would get the right answer maybe, some part of the time, but then a lot of the time it would fail, and you just wouldn't be able to explain why it got the answer that it would. Okay, whereas here the answers are or the wrong answers or the mistakes that it makes are much more understandable or intuitive as a person. Okay, and then just to say that this is what Stefan was talking about, the latest version of the competition of ImageNet. These are the top performing methods or groups, and basically they're all doing the same thing. Okay, so this is the exciting thing as well. There's lots and lots of code available. So remember, so this is I only did the top 4 or top 5. And remember, the previous year's result was over 10%, but now we have 5, 6, 7 groups who are, or we have Mr. Andrew Howard, who seems to be all by himself. So this means this is extremely exciting. This means that if you have a GPU card and an OK computer, and get your hands on the right data, and then learn a few of the tricks, you can be getting the same numbers. Okay, so in some sense, this machinery has democratized research in computer vision, and that can be scary or very exciting. Okay, so this is okay. So I suppose I can do a quick plug for the work, some of the more recent work, the work that we've been doing in our group. And this was our paper that I showed at the beginning, which was that we used one of the responses from one of the later layers in the CovNet, and then we just plugged it into an SVM to solve the visual recognition task. So basically, this is what I was talking about. This is somebody building some big, complicated visual recognition system, and then plugging, to build some feature representation of images or of objects. We just replaced it with a CovNet representation and got better results. Okay, so this is why people were either depressed or very excited. Okay, so this is just to make sure you understand. This is what I mean by we just took the responses from one of the fully connected layers. I think it was either this one or this one, but one of them, and just plug that into an SVM and the appropriate training data for a database. Okay. Okay. So these are the numbers again. So does anybody here do transfer learning or not? Or do people know what transfer learning is? Okay. So this might be interesting to some of you. So okay. So currently, if you want to train a very deep network, you're going to have lots of label training data, okay? Or if you want to train it from scratch, okay? So it's a bit of a stumbling block. If maybe what happens then if I have a visual recognition task that differs from my image classification? What should I do? Especially if I only have very limited training data, but I still want to use the best or a good deep CovNet representation. Okay, so we've shown in the previous work that if you train it with ImageNet, you still get quite a good representation. But is there a way that I can make it better? So the answer is yes, you can. So there's some tricks that you can use. So there's the terminology in transfer learning, which is the source task. And you can think of the source task as the task where I have lots and lots of label training data. But then I have a target task, which is the task that I actually want to solve. So how do you leverage the large amount of label training data that you have to help you solve the target task where I have a very limited set of training data? So we basically explored lots of factors here. So when in this diagram here, we show what factors that we looked at. Okay, so given, what about if you have a set of source tasks where you have lots of training data, which should you use to train your CovNet from scratch, from a random initialization? What should your network architecture be? Should it be extremely deep? Should it be extremely wide? etc. I know you're all vitally interested, but it should be written. So maybe while we were doing this, people were finding this out. So that's that. Should I change? If I have a source task which is different from my target task, should I stop early in my training? Is there a danger that I'll overfit? Another cliffhanger here. You can know as long as you're careful with your learning rates, you should never do early stopping in training. Okay. So the old school of if you were doing neural networks 10 years ago, 15 years ago, you should have always do early stopping so you don't overfit. That's not true anymore. Okay, so you should just keep on training as long as possible until you get tired. Okay, and then if you have a source component, then how do you use that? Now, how do you transfer that to your target task? So there's something called fine-tuning, and what basically that means is, say you've trained your network from the random initialization to solve your source task, then you can just pump in the whatever label training data that you have for your target task and just do stochastic gradient descent again. So then you have this, but you have a slight balancing act though, because you want to remember some stuff. You want your parameters to remember some stuff about the source task, but you want them to learn stuff about your new task, okay? But you don't want them to completely forget about your source task because you don't have enough data here for them to. It's like if you had a little patch of. Yeah, say you had a small patch of clothing that you wanted to give yourself a nice color or accessorize, is how so how do you best use this accessory? Okay, and then the question is, given that I have fine-tuned my network, how do I extract my representation from it? Which layer should I use? Should it be a convolutional layer? Should it be a fully connected layer? Should I do PCA, etc.? These types of things. Okay, so then you end up with your target CovNet representation. So if you go read our paper, skip this for. These are basically what we found, and now we've ordered the tasks. Well, at least the visual recognition tasks. This is the source task is say image classification, and then we order the target tasks according to their sort of distance from this target task. So in the sense of instance retrieval, when you're trying to find the same building or the same shoe, that's quite different from doing image classification. So that's quite far. Whereas if you want to recognize different species of bird, which is something called fine-grained recognition, that's somewhere in between instance retrieval and the source image classification. So these are the general principles that we found. So basically early stopping, you shouldn't do it. Fine-tuning, yes. But generally, this is a slightly unstable process. It works better the more label training data that you have. Network depth is as deep as possible, please. Network width. Basically, if your target task is close to your source task, you should make your network as wide as possible as well. But if you're going far away, you should not make it wide because there's probably a danger of overfitting. So this is. Or it's learning stuff that's not particularly useful for the task. And then which representation? You use the later layers if your target task is close to your source task, and you use the earlier layers if your target task is quite far away from your source task. This is interesting. Yeah. Okay, so this graph here just shows what performance gains you can get by fine-tuning or applying these guidelines. Okay, so let me explain this. So this bar shows the best performance of a non-ConvNet solution on a particular database. This shows the next bit is the performance of the best performing deep network that was trained on to do image classification. And then these are the gains to be made if you exploit the small amount of label training set and the guidelines that we've given here. So you can see, in some cases, you can actually make some gains here. So this is a way, if you have relatively small amount of label training data, that you can leverage this to help you solve a task, and you can leverage another task where you have lots and lots of label training data. Okay. Just one last final thing. So from the first fully connected layer of your network, you can actually regress to local spatial information. And this is really interesting because when you go from your last convolutional layer to the first fully connected layer, basically each response in a convolutional layer corresponds to some pattern in some relatively big subpatch in the original window. Okay, so yeah, some pattern in quite big window. But then when you go to the first fully connected layer, you you conflate all that information together because you're linking one response to all the patterns in all the different subpatches that you found in the image so far. Okay, but I'll skip this. But actually, even if you take the first fully connected layer, you can learn a regression function that goes from that fully connected layer to some other task. So here we tried to reconstruct the original RGB image with just a linear regression function. Yeah. Okay. So it was actually a linear regression function for every single pixel in the image. Okay. So you go from the first fully connected layer to one particular pixel and estimate the RGB value. So it's doing something. I mean, here you can see it lost lots of high frequency information, but there seems to be still some spatial information retained. Here, there's a similar type of regression function where we do some segmentation. So this is my image, goes from the first fully connected layer to a labeling, to each label of this 20 classes, and this is the background class. And a white means a high probability, it's not really a probability, but it's a probability of it being the background class, and dark. And here, this is a high probability of it being a cat pixel here, etc. So you can, it seems to have learned or retained some spatial information as well. So there's almost like a treasure trove of information in all the responses that you have. So the big question now is, how do you access this information to do lots of cool things? Okay, I'm going to stop here because it's you listened for far too long. So thank you very much. So hopefully.
Yes, thank you very much. No, it was very exciting, at least for me. I hope for many more people. Yeah, so we can ask a few questions, or we can break things down and start with the mingling, but I see some questions. Yeah. So let's try to keep them short. So we'll spend maybe some minutes on that. And then we also have some time for a little bit of input of like what we're going to do maybe next month.
Thank you for the talk. I was wondering, how did people come to the conclusion that local minima wasn't how the
Well, for a start, the most obvious is that you train this tomorrow. It's random initializations, and lots of people train lots of networks from different random initializations, get very similar performance. And also, there's the other thing that, to get the very high numbers in the image classification competitions, like that, people train ensembles of networks. So you basically are learning different networks, but they all have similar performance. There's basically that everybody can train them. That's I think Jan LeCun is now doing some research, sort of more theoretical research, to try and explore the cost function in a more systematic way. But I think the most obvious thing is that lots of people can train them and get similar performance, and you're doing this from a random initialization. So we're not all finding the same minima, basically.
So in statistics and when classifying data, there have been a few rule of thumbs maybe for how many data points you need for each parameter.
Yes,
Is there something you can say about that in deep learning?
No, there's not. I think there's probably a race among theoreticians. At the moment, I presume the problem is that theoreticians, what they can analyze is so much simpler than the huge models that were having years. So at the moment, they're not saying so much useful things. I think Stefan Milan and someone else, they're trying to come up with theoretical analysis, but it's not. I mean, the thing is, this is hugely over-parameterized, but because you have so much data, and then you do low learning rates and you do this dropout, you make sure you don't overfit. So, I mean, as Stefan said, it's a bit of a mystery why it works so well. So yeah, if you are a theoretician, then it's a difficult but a big problem.
Yeah.
Oh.
In this paper, you show that in a pretty clear way that you can, from a source task, learn the basics and then fine tune in a later stage for a specified task. But that part is also always supervised. I mean, you have a smaller set of images from a certain distribution of images that you post-train or you fine-tune network. But in a situation where you have, that in a separate task, the images are sampled from a different distribution, with much less variation. Do you know any applications where you manage to do unsupervised tuning in the later stage from a source task, where you train the basic knowledge and then manage to do? Imagine you have a photographer that always takes photos of dogs from distance and cats close up, and you have to get his images, and you want to transfer knowledge from different images to find a better understanding of this specific distribution.
In an unsupervised way.
Yeah, in an unsupervised
I haven't seen. I could conjecture ways to do it, but they might
be. Do you see the idea of the?
Well, I mean, you could imagine that you do some clustering or something on the responses that you get. Or you come up with your own labels somehow.
Yeah,
in an unsupervised way.
In a generative model, there's usually an easy way of sorry, swearing. But then you usually infer parameters at the same time as you're inferring class labels. It's a natural interpretation of the fine-tuning unsupervised. But there isn't really much research on similar approaches with convolution networks.
Not at the moment.
Right.
I mean, I think people are beginning to try and, if you want to estimate structured outputs, how to do that in this and have. I don't know so much about it, but I think that's the next big thing we're trying to do it. And I mean, and doing unsupervised learning is still sort of some people's holy grail. Okay, so I shouldn't give too much a negative response. I mean, if you could do it, it's great.
But that's mainly been in the early part. I mean, feature extraction. This is different because it's in the really later part.
But has everybody heard this quote by Vapnik, which is that you should not, during training, you should not try to solve a harder problem than you want to solve the test time. Okay, so you could imagine saying that if you want to solve unsupervised learning, you're trying to model all of the images where you actually only want to, say, differentiate between cat images and dog images. So why would you want to build a whole generative model for images when you just want to recognize processes? But maybe we can talk about it later.
Thank you.
Yeah.
What about adaptive step-playing?
Sorry?
Adaptive step-playing during the training phase.
Well, I mean, people use things like momentum and stuff like that. I mean, when you mean that, you mean the learning rate.
Yeah.
I mean, if you read the papers, people do not do. I mean, maybe you look at your validation error as well to see that. You use that. You look at that to help set your learning rate and to make it smaller. Especially if you saturate performance, then you make it smaller. Stuff like that. I think the thing is, there's much less. If you read lots of the neural network papers from a decade or 2 decades ago, there's lots and lots of things about how do I do the optimization and momentum and should I do second order methods and stuff like that. But now people don't care much less. It doesn't seem to be as important, basically, now that you have deeper networks and that you can just do stochastic gradient descent. As long as you, basically after each epoch, you just reduce by a factor of 10 your learning rate. I mean, what happens in the fine-tuning is what sometimes people do is that you don't really update your parameters earlier on in the network. Because as Stefan said, basically the filters that the first layer of filters that you learn always look the same, regardless of, as long as you have a sufficient amount of data, they always turn out to be more or less the same. Okay, so you don't bother retraining those or to change those. So it's only the later layers and how you stick things, the mid-level features together that changes. Okay.
What platform do you use? What tool?
Torch or journal.
Okay, so all the results so far we've got have been using Cafe. I think we're looking into Torch at the moment because they have ways of parallelizing GPU so that you can make training faster. So that's what we're at the moment. So I have trained with neural network with Torch. It seems quite nice, but only on a very small scale. So, yeah.
And what kind of hardware platform are you running?
Okay,
what kind of timescales for training?
Okay, so we have K40s, which NVIDIA were giving away K40s to academic institutions, and we were in there early, so we managed to get our hands on 6 or 7 of these. Now they've changed the rules that you can only get 1 per group. So. But let's say you wanted to build a very big network, say AlexNet or a bit bigger, and use all the training data. Maybe it takes a week to do. But obviously, there's the amount of training you don't have to use all the training data to get a good idea of how some idea or how a network is going to perform. Okay? So the increase in performance given training data, it doesn't saturate, but it definitely levels off at some point. So you can definitely get it. You don't have to train a huge network with lots of all the available data that you have to get something that works okay and to get a reasonable idea about if you think what something is going to make an improvement.
So if we're talking about one single graphics card and this size of problem, it's weeks.
Well, let's say a week. Yeah.
Okay, I have to stop it here. We can stick around a little bit longer. I think by the support if people have time, so we still have half an hour at least for mingling.
Okay.
Thank you very much.
Thank you.
So just 2 small notices. One is also in the agenda of democratization of machine learning with deep learning. I would like to democratize the cleaning up a little bit, but maybe during the mingling also taking some of the beer bottles and moving them over there. So that's one.
I was going to say, I think that's socialization. That's socialism as opposed to.
And the other one is that there is a really great event, which I was asked to promote by some friends also trying from Neo Technology. So anyone who's interested in more graph technology, it's one of my other fields of research. So I'm always very excited about graphs. But there is a graph day in Stockholm. So it's the 17th of March. It's a whole day of interesting stuff. Morning with talks, the afternoon with some training. I'm not sure if some of the Neo guys are here. Do we have some Neo guys? No?
Sorry.
Yeah. But anyway, the slides will be at the meetup as well, meetup page. But yeah, 17th of March, all day for free. So no reason not to attend. But yeah.
Thank you.
Sorry, I didn't mean to stop.
It's okay.